In this video, we'll talk through the lecture notes for section 2.2, the Cauchy problem for the wave equation. So once again, we're going to set up a Cauchy problem, which is a pure initial value problem, meaning no boundary conditions. That's because we're working on the entire real line, so there's no boundary. So we have the wave equation. The second partial with respect to t is proportional to the second partial with respect to x. And we also have some initial conditions. The initial position is given by f of x, and the initial speed is given by g of x for any given x. We saw before that the wave equation was hyperbolic. You can see that if you write it in this way. So a is equal to negative c squared, that's a lowercase c. B is equal to 0, and capital C is equal to 1. So you can work out the discriminant, and you see that it's 4c squared, which is positive. So that means that this is a hyperbolic equation. We know what the formula is for converting this hyperbolic equation into canonical form. We have it written down right here. Psi is equal to ax plus bt, and tau is equal to, well, before we wrote cx plus dt, but we've already got a lowercase c. We have an uppercase c and a lowercase c, so instead of putting a c there, I put a k, even though normally we would put a c. That's all right for us to do because we're going to substitute k equals 1 immediately anyway. That was part of the transformation. A was equal to 1, k was equal to 1, and we had these formulas for b and d. B was equal to minus capital B plus the square root of the discriminant divided by 2 times capital C. This is a capital C. So that C, these are all uppercase C's. So upper case C here and here. Now we saw that B was equal to 0 and capital D is equal to 4 times lowercase c squared. So these are lowercase c's here. And same with these. These are all lowercase. So anyway, that gives us our formula. We end up with a equals 1, b equals lowercase c, k is equal to 1, and d is equal to minus lowercase c. So that gives us this change of coordinates right there. So in this new coordinates, we can write our lowercase u as capital U in the way that we did before, and you can work through the computations. These are the same as before. You don't really have to work through them because we've already done it, but if you go ahead and compute the first partial with respect to x, and then the second partial with respect to x, you get this term as our second partial, and here's our first partial with respect to t, and here's our second partial here with respect to t. So if you plug those into the wave equation, into this equation here, and you simplify it, you get the canonical form, which in this case is just capital U or the mixed partial derivative of capital U. And we know that that's the case because that's the canonical form for a hyperbolic equation. So I didn't really have to do all of these computations. I just like to do it to make sure that we're doing it right. So anyway, the canonical form is capital U partial derivative c partial derivative tau is equal to 0. The mixed partial derivative is equal to 0. So what do we do with that? Well, that we can solve. Let's go to the next page here. So we're starting with the mixed partial is equal to 0, and we want to solve for capital U. We can just simply integrate one variable at a time. So first, we use the fact, so we're rewriting this capital U sub c tau as the partial derivative with respect to xau, and then the partial derivative of that with respect to tau, I think I said that wrong. The partial derivative of capital U with respect to c, and then we compute the partial derivative of that with respect to tau, and that's equal to 0. So we can integrate this expression with respect to tau. So it's equal to 0. So that means when you integrate with respect to tau, you're going to get a constant, although it's constant with respect to tau. So that means you might have a function of c. Now I'm calling it k here because, again, we've got too many c's. I suppose we've already used a k as well, so I guess this should be like a capital K or something. Maybe I'll just do something like that. Just make all these capital K's. That doesn't really matter either because we're going to change that. We'll be done with that letter momentarily. So the idea here is we have some function that we're integrating with respect to tau, but it's the derivative with respect to tau is equal to 0. So that means the original function, which in this case is the partial derivative of u with respect to c, that must be constant with respect to tau. So if we integrate it, there's not going to be any taus. There's just k, some constant function, but it's constant with respect to tau. It might still have some c's in it. Now, if we just want to do a little sanity check, we can just remind ourselves that if we differentiate this with respect to tau, this is the derivative with respect to tau of this constant function. At least it's constant with respect to tau. So that does equal 0. And this is exactly that. So at any rate, we end up with the partial derivative of capital U with respect to c is equal to some function capital K, which is a function of c. The next thing to do is we want to solve for capital U. So here we have the first derivative, or the first partial derivative of u with respect to c, so we just simply integrate with respect to c. And then we're going to have that capital U is equal to some integral of k. We don't know what k is, so we can't actually integrate that, but this is just going to have a bunch of c's in it. But there's going to be some constant with respect to c. So we have to introduce a function which is a function of tau. So we're going to use the fundamental theorem of calculus to write this indefinite integral as a definite integral, because this indefinite integral is an antiderivative. It's the general antiderivative. So we're going to write it in terms of a definite integral in the way that we usually do, which we have here. So this is the definite integral from 0 to c of k at some other variable, some dummy variable, which I'm calling z, but you could call it anything, as long as it's not something we've already used. Now we have to add in some initial condition, essentially, some constant of integration. That constant of integration might depend on tau. So again, if you, let me just highlight this. So if you differentiate this with respect to c, this definite integral from 0 to c, capital K at our dummy variable z dz plus psi of tau, if you differentiate this with respect to c, of course, by the fundamental theorem of calculus, this definite integral becomes capital K at c, and this psi is a function of tau, so if you differentiate it with respect to c, that term goes away, and you're just left with capital K at c, which is exactly what we wanted to get. It's this term right here. That's that term right there. So we have that u, capital U, is equal to this function of psi, so we're just going to of xi rather, well, xi, however you want to say it. So we have that capital U is equal to this function of xi. So we're going to give it a new name. We're going to call it phi, or phi of xi. And we have this constant function, this constant term here. It's constant with respect to xi, so it's some psi of tau. So what we've established is that this capital U is equal to some function of xi plus some function of tau. So that means we have a solution for capital U. If you have a solution for capital U, you can always change your coordinates back to xt and get a solution for lowercase u, because lowercase u, of course, is equal to capital U at the transformed variables x plus ct, comma x minus ct. So what does that give you? Well, this term right here, the x plus ct, this is our psi, and this x minus ct, this is our tau. So we have some function of xi plus some function of tau. So the function of xi is this phi, and that corresponds to this term right here, plugging that in. And then we have a function of tau. So this function of tau corresponds to this term right here, where tau is equal to x minus ct. So what we've established is we've established a general solution for u. It's a function phi, some function phi at x plus ct plus some function psi at x minus ct. So we just notice that that's a left traveling wave plus a right traveling wave. So the solution of u, the solution for u of the wave equation, in this Cauchy problem, is a left traveling wave plus a right traveling wave. Now this is the general solution. We haven't used the initial conditions yet. These initial conditions are what will give us what phi and c actually are. So our initial conditions are that the initial position is given by this function f, and the initial speed or velocity is given by this function g. Okay, so how are we going to make use of these? Well, we know what u is now. U is right here. It's phi plus, or phi evaluated at x plus ct plus psi evaluated at x minus ct. So let me just rewrite that here so that way we can easily see it. What we want to do is we want to compute u at x comma 0, but we also want to compute the derivative of u with respect to t. So here we have u. It's phi at x plus ct plus phi plus psi at x minus ct. Notice that phi and psi are each functions of one variable. So when we compute the partial derivative of u with respect to t, we need to use the chain rule, but we're differentiating these functions of one variable. So the derivative of this term is going to just be phi prime evaluated whatever's inside. But then of course we have to multiply by the derivative of what's inside, the derivative with respect to t. So if we're differentiating x plus ct with respect to t, that's where the c comes from. So the derivative with respect to t of x plus ct, that's where that c comes from. And over here, if we differentiate this psi, we're going to get psi prime, but we have to multiply by the derivative of what's inside with respect to t. So here we have the derivative with respect to t of x minus ct, and that of course is minus c. So that's this term right here. So let me just, so this c corresponds to that c, and this negative c corresponds to this. That's a little hard to actually make out, so let's just underline it like that. So might as well be consistent, just underline that one as well. Okay. So now we have u at xt and u sub t at xt. So to get the initial conditions, we just simply plug in t equals 0. So for u at x0, you just lose the c of t terms, and you just end up with phi at x plus c at x. C at psi at x. Now this we know is equal to f. So this f right here is that f. So that's u at x0, u at x0. And then we have the partial derivative at t equals 0, that's this term, is going to give us gx. Now once again, you're just going to lose the terms in the middle that have a ct. So we're just evaluating at t equals 0. So you lose that ct term right there, and that ct term right there. So you end up with c times phi prime at x minus c times psi prime at x. There you go. And this is equal to our g. So these initial conditions give us two equations. We have phi at x plus c of x equals f of x, and we have c at phi prime of x minus c at psi prime of x equals g of x. So we have two equations. We want to figure out what phi and psi are. So there are a couple of different ways you can do this, but what I did here was I first took this first equation. Let me just label that 1 and label this one 2. So the first thing I did is I took that equation I labeled 1 and I differentiated both sides. So differentiate both sides of 1. If you do that, you end up with, on the left, you end up with phi prime at x plus psi prime at x. So that's the derivative of this term. And then on the right, you have the derivative of f, which is that f prime. Now, this second equation, all I did was divide both sides by c. Divide by c. And the value of that is now we have two equations with two unknown functions. One is phi prime and the other one is psi prime. Notice here we had a phi and a psi, and here we had a phi prime and a psi prime. So now we have phi prime and psi prime in each one of these. So we have two equations with two unknowns. It's just those unknowns happen to be functions, but this is for an individual x. So what you can do is you can simply solve for phi prime and psi prime now. The first thing that we did here is we added these two equations together. So if you add the two equations together, then notice that the psi prime terms cancel, and then you end up doubling this phi prime term. And then you have the sum of these two terms. So you have f prime of x plus 1 over c times g prime, and that's what we have here. Not g prime, just g. So you have this f prime of x, that's this f prime of x, plus 1 over c g of x, which is right there. Now let me get rid of all of these extra superfluous lines here and whatnot. So again, let me just highlight these. So we have this f prime term is right there, and then we have this 1 over c g prime is there. So we just added the two equations together. So add 1 and 2, and that gives you this one. Of course, actually what it gave you was the 2 there, but then we divide by 2, and that's where that 1/2 comes from. So then we do the same sort of thing, but now we subtract. We subtract. So it's 1 minus 2 to get this one. So if we subtract, then the phi prime terms go away, and then you end up adding these because it's psi prime minus a negative psi prime, and that gives you 2 psi prime here. Then we're just going to end up dividing by the 2 to get that 1/2 again. And then again, we're subtracting these terms, so you have f prime minus 1 over c g at x. So that's what you get if you subtract them. So now we know what phi prime of x is, and we know what psi prime of x is. And so if we want to determine what phi and psi are, we just simply integrate. So let's integrate phi prime. That gives us phi. So we're going to have this 1/2 term right there. You integrate f prime, that gives you f, and then you integrate 1 over c g at x. Now this isn't a derivative, so we don't have a name at the moment for the antiderivative of g, so we just write it as the integral of g of x, like this. Now we do the same thing for psi prime. You integrate psi prime and you get psi. So that 1/2 goes to here. You integrate f prime to get f, then you integrate this g and you get the integral of gx dx again. It's just some antiderivative. Now there's a 1 over c term here and a 1/2, and we have to distribute that 1/2. That's why there's 1 over 2c here. It's 1/2. So let me just see if I can find another color here. So this 1/2 we distribute here and here. And same with this 1/2. We distribute it here and here. That c, that's this c right here, that's this c right there. So that's where all those terms come from. Now the next thing we do is the same thing we usually do. We take these indefinite integrals and we write them as a definite integral. So I just picked some dummy variable s. So the antiderivative of g By the fundamental theorem of calculus, the antiderivative of g is going to look like this. This is a particular antiderivative plus some constant term. So you'll have a different constant for each one of these. But we have some constant term here. So it's the integral from 0 to x of g at s ds plus some constant term. So let's go to the next slide, or the next page, and you can see that we've just rewritten it out like that. So phi of x is equal to 1/2 f at x, that's this term, plus 1 over 2c, and then it's this antiderivative, which is the integral from 0 to x of g of s ds, and then some constant. Now there's already a constant here, but if you distribute that constant to this constant, it's just going to be some other constant. So this c1 is 1 over 2c times whatever constant was here. And then you have the same sort of thing for psi. It's 1/2 f minus 1 over 2c times this antiderivative, which is, so it's just the integral from 0 to x, g of s ds, plus some constant of integration. Now this c1 and c2, these are arbitrary constants. However, we can actually identify what they are by looking at our initial conditions. So the first thing to do is to just rewrite u. So u at x comma t is phi at x plus ct plus psi at x minus ct. So here's phi is right here, and the psi term is right there. Okay, so we're evaluating this at x. This first one, we're evaluating at x plus ct. So any place we see an x, we replace it with x plus ct. So x plus ct goes here. So there's an x plus ct there. There's also in the upper limit of integration, that's an x plus ct. Now for psi, this one, we're replacing all of these x's with x minus ct. So there's an x minus ct goes there, and then in our upper limit of integration, which is right here. Now what I've noticed here is that we have a minus sign, and we have the integral from 0 to x minus ct. So you can just flip that and it becomes a plus. So it becomes a plus 1 over 2c, and then the integral is flipped. So instead of going from 0 to x minus ct, it's from x minus ct to 0. So I just did that for convenience, because the first thing we can notice, if I go back to this color, so we have this 1/2 f plus ct, that's right here, together with that 1/2 out in front. And then we have a similar term. We have this term, f 1/2 f at x minus ct, that goes right here, with again with the 1/2, like that. And now we can combine these two integral terms. Notice they both have a 1 over 2c in front. So we have a 1 over 2c here, and we're actually combining it with this one, 1 over 2c, so that's 1 over 2c there. And now this one, this is the integral from 0 to x plus ct, and this one's x minus ct to 0. So if you add those two together, you get the integral from x minus ct to x plus ct. So you have that here, plus some constant. Now here, notice I have some constant here, c3. c3 is equal to c1 plus c2. c1 plus c2 is c3, because we're just adding those two together. If you add together two arbitrary constants, you get another arbitrary constant, c3. So I'm just going to call it c3. So that's where that c3 comes from. Okay, well, we can figure out what the value of that c3 is by looking at our initial condition. So we know that u at x comma 0 is equal to, well, we just plug in t equals 0 here, 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 and here, just in those 4 places. And you get the 1/2 out front, that's this 1/2. And then you get the f, so we're just replacing t with 0, and so you get f at x. And here you get another f at x. So this is 2f of x divided by 2, so you just get f at x. And then over here, what happens when you replace t with 0, you get the integral from x to x. And of course that term, if you're integrating from x to x, that's just going to give you 0. Plus our constant of integration, c3. So, but what is this supposed to equal? This is our initial condition. u at x comma 0 is equal to f of x. So we get that u at x0 is equal to f at x plus c3 is equal to f of x, so c3 must equal 0. So that gives us our solution to the Cauchy problem for the wave equation. This is known as D'Alembert's formula, and this is the solution we were looking for.